To be a good mathematician, one must be curious and open to learning from the world around us. S.S. Chen, or Shiu-Sung Chen, is celebrated as one of the greatest mathematicians of the 20th century, particularly in the field of geometry. His contributions, especially to differential geometry, have influenced not only mathematics, but also fields like theoretical physics. Today I will explore his remarkable life, his groundbreaking work, and the lasting impact he has had on the mathematical world. Born on October 26, 1911, in Jiaxing, China, Chen showed a profound aptitude for mathematics from an early age. His journey began at Tsinghua University in Beijing, where he completed his undergraduate studies before moving to Europe to further his education. Chen's academic path led him to Germany, where he pursued his PhD under the guidance of the eminent mathematician Élie Cartan. Cartan, a towering figure in geometry, inspired Chen to delve into differential geometry, a field that would become Chen's lifelong passion and in which he would make his most important contributions. Differential geometry, for those unfamiliar, is a branch of mathematics that uses tools from calculus and algebra to study the geometry of curves, surfaces, and spaces. It plays a pivotal role in understanding complex structures in both mathematics and physics, from the shape of the universe in general relativity to the behavior of fields in quantum mechanics. Chen's work in this area revolutionized the way mathematicians approach geometry. One of his most famous achievements is the creation of Chen classes. Developed in 1946, Chen classes are fundamental invariants that describe the curvature properties of vector bundles. A vector bundle is essentially a collection of vectors associated with a geometric object, and Chen's classes provide a way to measure how these bundles twist and curve. S.S. Chen's development of Chen classes stands as one of the most profound contributions to modern mathematics, specifically in the areas of differential geometry, algebraic geometry, and topology. Chen classes play a critical role in understanding the intrinsic geometry of spaces and how they can be classified through their curvature and topological properties. To truly appreciate Chen's contribution, we must first delve into what Chen classes are, their origins, and their far-reaching impact across multiple branches of. In simple terms, a Chen class is a way to measure the curvature of a vector bundle. A vector bundle is a mathematical structure that consists of a base space, like a surface or a manifold, and a collection of vectors attached to each point of that space. These bundles allow us to study how geometric and algebraic structures vary across the base space. For example, think of a sphere with a tangent plane attached at every point. The collection of all these tangent planes forms what mathematicians call the tangent bundle. Now imagine trying to measure how these tangent planes twist as you move across the surface of the sphere. Chen classes are the mathematical tools that quantify this twisting or curvature. Chen classes are part of a broader family of characteristic classes, which are used to describe the geometric and topological properties of vector bundles. However, what makes Chen classes special is that they specifically deal with complex vector bundles. Vector bundles where the fibers, the vectors attached to each point, are complex vector spaces rather than real vector spaces. Complex geometry often has richer and more intricate structures than real geometry, which is why Chen's work became so significant. Before Chen's work, mathematicians already had tools like the Euler class and the Stiefel-Whitney class to describe the geometry of vector bundles in real spaces. These classes were useful for understanding the topology of real vector bundles, but there was a gap when it came to dealing with complex vector bundles, structures that are far more prevalent in advanced mathematics and physics, particularly in the study of algebraic varieties and complex manifolds. In 1946, Chen introduced his Chen classes as a natural extension of these earlier tools, but for complex vector bundles. His approach unified differential geometry and algebraic topology, providing a way to systematically classify and understand the curvature and topology of complex geometric structures. Chen classes are defined using the curvature of the vector bundle's connection, a mathematical structure that helps us differentiate vectors as we move along the base space. This approach allowed Chern to compute these classes from the curvature tensor, providing an elegant and systematic way of understanding the global properties of a vector bundle based on local geometric data. One of the most remarkable applications of Chern classes is Chern's extension of the classical Gauss-Bonnet theorem. In its classical form, the Gauss-Bonnet theorem connects the total curvature of a surface to its Euler characteristic, a topological invariant that provides important information about the shape or structure of a surface. Chern extended this result to higher dimensional complex manifolds using his Chern classes. His Chern-Gauss-Bonnet theorem generalizes the idea, linking the curvature of higher dimensional manifolds to topological invariants, specifically the Euler characteristic, but in a much broader and deeper context. This result was groundbreaking because it connected geometry and topology in a new way, allowing mathematicians to compute topological invariants of high-dimensional spaces by using geometric information like curvature. In algebraic geometry, Chern classes are invaluable. They provide a way to understand the intersection theory of algebraic varieties, a central topic in the field. Intersection theory involves studying how geometric objects intersect and what properties arise from these intersections. Chern classes offer a means to classify and understand these interactions. One key application is in the classification of vector bundles over algebraic varieties. For instance, given an algebraic variety, which is essentially a space defined by polynomial equations, Chern classes can tell us how vector bundles over these varieties behave, offering insights into their curvature, global sections, and other geometric features. Chern's work also laid the foundation for what would later become the study of moduli spaces of vector bundles. Moduli spaces are spaces that classify all possible vector bundles, or other geometric structures, on a given manifold, and Chern classes play a central role in understanding these spaces. This is crucial for many modern developments in algebraic geometry, especially in relation to the Langlands program and the theory of motives. In modern string theory, Chern classes are used to describe the geometry of the space-time manifold on which strings propagate. They help physicists understand how the curvature of these higher-dimensional manifolds influences the behavior of strings, making Chern's work directly relevant to some of the most cutting-edge research in fundamental physics. S.S. Chern's introduction of Chern classes transformed the way mathematicians think about the geometry and topology of complex spaces. His work provided powerful tools to bridge different areas of mathematics, from algebraic geometry to topology, and continues to inspire research in both pure mathematics and applied fields like physics. Chern's ideas have permeated far beyond their original context, shaping the study of moduli spaces, complex manifolds, and even quantum field theory. Chern classes remain one of the most important tools in modern geometry, providing deep insights into the structure of spaces and their curvature. Beyond pure mathematics, Chern classes have found applications in theoretical physics, particularly in gauge theory and string theory. In 1974, Chern collaborated with physicist James Simons to develop the Chern-Simons theory. While this theory initially arose in the context of pure mathematics, it has since become a cornerstone of modern theoretical physics. At its core, Chern-Simons theory provides a topological quantum field theory, TQFT, that captures the behavior of gauge fields in a three-dimensional space. The theory is defined through a Lagrangian, which involves a Chern-Simons term constructed from a gauge connection and its curvature. This formulation reveals how gauge invariance leads to rich topological structures, allowing physicists to extract invariant quantities related to the geometry of the underlying space. One of the most significant aspects of Chern-Simons theory is its application to knot theory and quantum field theory. The theory provides a powerful tool for understanding how knots and links in three-dimensional spaces can be characterized by topological invariants. In this context, the Chern-Simons invariants can be used to distinguish different knot types, demonstrating the deep connection between topology and quantum physics. Chern-Simons theory has also found applications in condensed matter physics, particularly in the study of fractional quantum Hall states. In this realm, the theory helps describe the behavior of electrons in a two-dimensional system subjected to a strong magnetic field, leading to phenomena such as anyonic statistics. Moreover, the Chern-Simons action has inspired the development of other theories, such as topological field theories and string theories, highlighting its importance in modern theoretical physics. The interplay between geometry, topology, and quantum field theory through Chern-Simons theory continues to shape our understanding of fundamental physical phenomena. S.S. Chern's legacy is vast, not only because of the specific results he achieved, but because of the way his work bridged different fields of mathematics and connected mathematics with physics. His ability to see deep connections between seemingly disparate areas allowed him to solve problems in ways that have influenced generations of mathematicians and physicists. Beyond his research, Chern was also a dedicated educator and mentor, contributing to the global mathematical community through his work at universities in both China and the United States. In 1985, in recognition of his immense contributions, Nankai University in Tianjin, China, established the Chern Institute of Mathematics, in his honor, further cementing his impact on the field. Chern passed away in 2004, but his influence continues to be felt. The tools he developed, particularly Chern classes and Chern-Simons theory, remain fundamental in both mathematics and physics. His work has provided the mathematical foundation for many modern theories, including string theory, and continues to inspire researchers exploring the intricate relationship between geometry and the physical world. Chern's vision of mathematics as a unified discipline, where algebra, geometry, and topology intersect and enrich one another, remains a guiding principle in contemporary mathematical research. Through his pioneering work, S.S. Chern has left an indelible mark on the mathematical landscape, and his legacy will continue to shape the field for years to come. Thank you for watching, and I hope this brief exploration of S.S. Chern's life and contributions has provided insight into the profound impact of his work on mathematics and beyond.